We're still in this section of the definition of the derivative. I promise that tomorrow you can start using the shortcut. Today is actually something I did not teach you yesterday, but it's an alternate form of the derivative. Okay, last night we used the limit as h approaches 0, f of x plus h minus f of x all over h. To find f prime of x. And what that did was it gave us a general formula to find the slope at any point. And then if I wanted to find the slope at a specific point, then I plugged in that x value into f prime of x. All right, well, the alternate form of the derivative actually does both of those things at the same time. So if you're only interested in finding the slope at a specific point, at a specific x value, then you can use the alternate form of the derivative. So the derivative at a specific point c is the limit as x approaches c of f of x minus f of c over x minus c. And it's actually a little bit easier formula to deal with. There's not as much algebra that's involved. Now, that's provided that the limit exists. And in order for the limit to exist, it requires the left and the right side limits to be the same. We learned that in Chapter 1. Those one-sided limits are actually called the derivatives from the left side and from the right side. And we'll come back to that in just a second. All right, so I'm going to use the alternate form of the derivative to find f prime of x at a specific x value if it exists. So number one, f of x equals x squared plus 2x, and I want to find the derivative at x equal 1. Now, yesterday, you would have had to have done the whole big thing up here, this formula, and then plugged in a 1 for x. Now we can do it all in one step and use the alternate form. So the alternate form would be, I'm looking for f prime of 1. Bless you. And that equals the limit as x approaches 1. F of x, which is just given to me, x squared plus 2x, minus f of c. Well, in this case, f of c is f of 1, which f of 1 would be 3. And then divided by what? X minus 1. Good. So on top, I took f of x minus f of 1. Okay, now if I plug in 1, I get 0 over 0. But what do you think I can do to this to help me out? Factor. So the limit as x approaches 1 was going to factor into x plus 3, x minus 1. Over x minus 1, and the x minus 1's cancel. So that limit is 4. So what I've just found is that f prime of 1 equals 4. The slope of f of x when x equals 1 is 4. So a little bit shorter than what you had to do last night, maybe? Okay. All right. But what I'm mainly going to use the alternate form of the derivative for is to prove why some limits don't exist. So let's start with f of x equals funky bracket x. Anybody recognize what that function is? It's the stair-step one. Very good, okay? It's that stair-step function. It's the greatest integer function. And what it means is, if I take the greatest integer of, say, 1.2, it means the biggest integer that's not bigger than 1.2. So what would that be? 1, right. How about negative 5.3? Biggest integer that's not, my hand is sweaty and this is freaking out. The biggest integer that's not bigger than negative 5.3, it's negative 6. Negative 5 is bigger than negative 5.3. It's basically, if you think about a number line, it's always going to be the whole number on the left of the number line from whatever number is given to you. Okay, so anyway, that's what this graph looks like. All right, so what I'm interested in is f prime of 0. So I want to take the limit as x approaches 0. F of x is just that greatest integer function. Minus f of 0. So the greatest integer that's not bigger than 0 is 0. And then divided by x minus 0. So I'm really trying to find the limit as x approaches 0. Greatest integer function of x over x. Now, we don't really know how to take that limit algebraically, so we're going to use our calculators. So use the table in your calculator to find that limit. All right, that greatest integer function, the way that you access that is under the catalog. So go to catalog, and it's under int for integer. So when you hit the catalog button, you're already in alpha mode, and where's the I button? 9. And if you scroll down to that int, there it is. This is not something that's going to come up on a test. So, all right, so the greatest integer function of x divided by x. All right, now I'm going to use the table to find that limit. So I want to go to table set. And I want to start my table at 0, because it's the limit as x approaches 0, and I want for my delta table to be pretty small. I'm going to do 0.001. All right, so what can you tell me about the limit as x approaches 0? It doesn't exist, because from the right side, looks like I'm probably approaching 0, but from the left side, I'm approaching infinity. So since those left and those right limits don't match, the limit does not exist. All right, well, if the limit doesn't exist, so this limit does not exist, therefore, f prime of 0 does not exist. Because that whole limit was actually to help me find f prime of 0. Now, the reason that the limit does not exist at x equals 0, if you look at the original graph of the greatest integer function of x, is because f of x is discontinuous at x equals 0.
The whole reason we plugged it into our calculator was because the limit is x approaches 0 is that doesn't,
So anywhere a function is discontinuous, the derivative will not exist at that point. Okay, let's look at number 3. Okay, let's find f prime of 2 for number 3. So I'm going to take the limit as x approaches 2 of f of x, which is the absolute value of x minus 2, minus f of 2. What's f of 2? 0. Okay, it's kind of nice. Zeros are always good in math, in my opinion. And then divided by x minus 2. Now, does this limit, have I asked you to find this limit before or something very similar?
Yes.
Yeah. It doesn't exist, right, because it's that So that graph of absolute value of x minus 2 over x minus 2 looks like this. So the limit, once again, does not exist. So if the limit doesn't exist, then f prime of 2 does not exist. Absolutely. On a test, if you wanted to plug this into your calculator and look at the table or look at the graph, absolutely. I just was trying to save a little bit of time, and I figured a couple of you would recognize that. All right, now, the reason that this limit doesn't exist, what does the graph of the original f of x look like? Good, Celeste. Okay, what letter of the alphabet? A V. Good. and it's been shifted to the right 2 units. So this looks like kind of what was on the homework. Gosh dang it. What was on the homework last night. What this is called right here at this point, it's called a cusp. And it's a sharp point. And the derivative will never, ever exist at a sharp point. And I kind of went into it on the homework, but the reason is that derivative is slope. So the slope on the left side of this graph is -1. And then all of a sudden, with no warning whatsoever at x equal 2, it changes to +1. So it's not a gradual change. It's just the sudden change from a slope of -1 to +1. Tamara? Okay, good. And don't get confused. Okay, this right here is the graph of f of x. Sorry. Good. The limit on the alternate form of the derivative graph does not exist. And that tells us that the derivative does not exist. But if you're just talking about the graph of plain old f of x, then yeah, that limit would exist. But that doesn't have anything to do with the derivative at that point. Yes, and any other point would have the derivative. Exactly. Okay, there's one more reason why a limit doesn't, or a derivative doesn't exist. So, and we're going to illustrate it with number 4. All right, so on number 4, I'm wanting to find f prime of 0. So we're going to take the limit as x approaches 0. F of x is x to the 1/3. F of 0 is 0. And then over x minus 0. So it's the limit as x approaches 0 of x to the 1/3 over x. You could just type that into your calculator the way that you see it. Or is there a way to simplify x to the 1/3 over x? Okay, x to the -2/3. So the limit as x approaches 0 of x to the -2/3 would actually equal 1 over 0, because x to the -2/3 is 1 over x to the 2/3. And when you plug in your 0, you get 1 over 0. All right, 1 over 0 means an infinite limit, or more importantly, it just doesn't, that limit does not exist. So because that limit doesn't exist, the derivative does not exist at that point. The reason that the derivative does not exist at that point is that this is what the graph of x to the 1/3 looks like. And at x equals 0, there's a vertical tangent line. Yeah, the slope, there is a tangent line that exists, but the slope of that tangent line is undefined, which undefined really doesn't exist. So that's kind of weird. All right, so to sum that up. All right, a function is not differentiable at x equals c if you've got, for 3 reasons. 1, f is not continuous, f has a cusp, or it has a vertical tangent at x equals c. You need to know those 3 reasons that a function might not be discontinuous or might not be differentiable. Part of your homework tonight is just looking at a graph and saying where the function is not differentiable. So if you see a place where the graph is discontinuous, it's not differentiable. If you see a cusp, it's not differentiable. If you see a vertical tangent, it's not differentiable. And on a vertical tangent, they will usually draw in a dotted line for you to kind of signify that that's a vertical tangent line. All right, a theorem. If f is differentiable at x equals c, then it's continuous. So if I ever tell you that a function is differentiable, you need to think, ding, 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 that also means it's continuous. Yes, but I could say it's differentiable everywhere, and therefore it would be continuous everywhere. So differentiable implies that a function is continuous. But if a function is continuous, does it automatically imply that it's differentiable? No. Because, is this a continuous function? Yes, it's continuous, but it's not differentiable at the cusp. Differentiable means you can take the derivative. Okay, look at this multiple choice question. If f is a function such that the limit as x approaches a of f of x minus f of a over x minus a equals 0, which of the following must be true? What is this a formula for? The derivative. The derivative at what x value? A. So this is basically saying that f prime of a equals 0. So is that a choice? Yes. And there will always only be one right answer to a multiple choice question. Okay, try number 2 on your own. Or right. Okay, so what do you think for number 2? It is C. Good. This was the original limit definition that we learned yesterday, but basically instead of an x, they replaced it with an a. And you need to know that definition forwards and backwards where you can replace it with any variable that you want. This is the alternate form that you learned today. What is wrong with number 3? It shouldn't be x approaches 0. It should be h approaches 0. Right.